Alright, welcome back to another video. In this one we're going to be looking at the gravitational field strength G, or little g as it's known. What we've covered so far in a lot of physics videos is we have looked at a field as a concept, as a region of space in which an object experiences a force. And we've come across the electric field, we've come across the magnetic field, and then of course we have the gravitational field. And when we represent those, we represent them with lines, and those lines have a variety of features in common. The first thing, if this is a circular object we're going to be talking in terms of the gravitational field, is that these lines extend like this, and for gravity the arrows are going in. So what that means is that that force is an inward acting force to the center of the object. If we were talking about a point charge, then the arrows would go in the direction in which a test positive charge would be. And if it was the magnetic field, it would be the direction in which a test monopole of north pole would go. But here we're talking about the gravitational field strength, and so therefore they go in the direction towards the center of the object. One thing we can realize about this is that the density of the lines indicates the magnitude or strength. So here they're closer together, so we have a stronger field. And as we move outwards, they're further apart, therefore we have a weaker field. And that sort of makes sense because we do know that the further you go away from the surface of the Earth, the weaker the gravitational field strength is, or gravity is. Now, what's something else we can learn from this diagram here? Well, if we have this surface of the Earth, because the Earth is so big, when we look at the surface of the Earth, pretty much the field lines are parallel. Okay, so if we imagine this as being the Earth, when we get down to the surface of the Earth, pretty much the gravitational field lines are parallel. Okay, so when you drop an object, it falls perpendicular to the surface of the Earth. So in terms of how we can describe G, we can describe it in two ways. So we can describe it in terms of the strength of the gravitational field. And when we do that, it's 9.8. The value is 9.8, the magnitude is 9.8, but the units is newtons per kilogram. So when we're using G in terms of describing the strength of a gravitational field, it's newtons per kilogram. Now of course that makes perfect sense because when we do the good old Fg equation is equal to ma, and we know that A is the G in this instance, well, mass is measured in kilograms. Gravity, the constant here, the gravitational strength, is measured in newtons per kilogram. The kilograms cancel, and therefore our final answer is newtons. So when we are working out, for example, our weight, when we work out our weight, the weight is equal to mg, and so therefore our final weight would end up being a newton units, right? Sounds a bit weird, but the unit that we use is newtons. The other way in which we can describe G is in terms of the acceleration. We can describe it in terms of the acceleration of a body in a field, and we have 9.8 for Earth, and that's meters per second squared. So they're the two different ways in which we can use our gravitational field strength. We can use it in terms of the acceleration of a body, acceleration due to gravity, or we can measure it in terms of the strength of the field in terms of newtons per kilogram. So make sure you get all that down, and we're going to talk about this concept a little bit more. Now, in terms of gravity, we've talked about Newton's universal law of gravitation. It was capital G, the universal gravitation constant, m and m of the second body all over r squared. So if we also know that Fg is equal to ma, we'll make this equal to ma here. So we end up with that equation there. Now when we're saying ma, we really mean, of course, acceleration due to gravity, so we'll make that g. And the m's cancel. So what that means is that we can express g of a particular body in terms of the gravitational constant, the mass of that body, divided by r squared. And so we can see here that the value of g is proportional to the mass of the body. So the value of 9.8 meters per second squared on Earth is dependent upon the mass of the Earth. If we make that mass smaller, such as the Moon, then if the mass is smaller, therefore g is smaller, and it is. It's 1/6 the value of the Earth. It's also inversely proportional to the square of the distance. We knew that when we looked at this equation up here, the square of the distance between the two objects there has an impact on the force experienced by those. But g also varies by the square of the distance. So I'm standing on the surface of the Earth now. If we elevate ourselves and go further and further and further away from the center of the Earth, then g, the value of g, will decrease. Okay? So that is that there. Let's do a calculation. So let's do the calculation for Earth. So g for Earth, we put some values in. We know that capital G is 6.67 times 10 to the minus 11. Well, what is the mass of the Earth? Well, we're going to say 6.0 times 10 to the 24 kilograms. Okay, sometimes it'll be a little bit more accurate than that, or 5.89 or 5.9. We're going to use 6. And what is the radius of the Earth? So let's plug those values into our equation here. So we've got G, 6.67 times 10 to the 11, times that by the mass of the Earth, and the radius. And when we do all those calculations, it comes out to be 9.8 meters. Sorry, 9.8, and we could express that as in newtons per kilogram if we're talking about the strength of the field. If we're talking about the acceleration of an object in that field, 9.8 meters per second squared. So for Earth, it's 9.8. Let's do a calculation for the Moon. All right, so you can see here that the Moon and the Earth there, obviously the distance between them is not to scale, but to give you a size comparison of the Moon and the Earth, let's do a calculation of g on the Moon. Remember that on Earth, it's 9.8 newtons per kilogram, or meters per second squared. So when we plug this in here, let's see what we get. All right, so we can see there we've got 1.62, which is 1/6 the value on Earth. So the Moon, a lot smaller, and therefore because it's smaller, has less mass, and the radius is smaller, it turns out to be 1/6 the value for Earth. Now, this value that we have for Earth, 9.8, is not constant. It varies for a lot of things. The first thing it varies for is distance. As we just said, because it's over r squared, it's an inverse square law. So the further you go away from the surface of the Earth, right, up an orbit, the value for in a satellite is a lot different to when you're on the ground. If you're up on a mountain, the value that you experience there for g is a lot different to when you're on the surface of the Earth, because you're further away from the center of the Earth. So distance is the first thing. Where you are located on the Earth, or whether you're in orbit or not, depends, gives you a different value for g. The second thing is the density of the crust. So depending upon where you are, you may be standing on some crust that has some really highly dense geological rock formations, and therefore that's going to give you a slightly different value of the acceleration due to gravity. Or if you are in a region where the rock is not as dense, it's a less dense sedimentary rock, for example, that's going to change the value for g as well. What's another reason? Well, another reason is the shape of the Earth. So the poles and the equator. So the shape of the Earth is not a specific. All right. So the shape of the Earth is not a perfect sphere. Okay, it is slightly bulged. If I can sort of do this, slightly bulged across the equator. So the equator is a little bit further out from the center of the Earth compared to the poles. So that means the value of g around the equator is a little bit higher, and it's a little bit less on the poles due to the Earth not being a perfect sphere. So if you want to, weigh yourself, don't go to the equator, go to the poles, and your weight will be a little bit less because of the fact that g is a little bit less. So there's some variations in how G is around the Earth. That's it for this video. Hopefully that makes sense to you. You have a better understanding of what gravitational field strength means, that it can be used for both the strength of the field in newtons per kilogram, or describing the acceleration of a body in meters per second squared, and it changes depending on these factors here. All right, see you in the next video.